Today we are going to talk about rates of change and the slope of a curve. In grade 9, you learned that the slope of a line is the coefficient of the x variable in the slope y-intercept form of a line. If you remember, the slope y-intercept form of a line was y is equal to mx plus b, where m was the slope and b was the y-intercept. In this unit, we are going to rename the slope as the rate of change. This indicates how fast a variable y changes when the variable x is changing. Now, the slope or the rate of change can be seen almost everywhere. For instance, when you throw a ball upward, the height of the ball changes as time changes. Your height also changes with your age, with the time. The price of a stock changes as time goes on. Another example is the surface area of a sphere changes when the radius or the diameter changes. These are all examples of rate of change or the slope. We learned in grade 9 the slope was defined as y2 minus y1 over x2 minus x1. This was defined as the slope of a linear function. Now you may ask, when we are dealing with a function which is not linear, like a rational function or quadratic, how are we going to define the slope or the rate of change? To be able to define the slope or the rate of change for any type of function, we are going to define a new term called secant. A secant is a line which joins 2 points on a curve. For example, in this function, you can see it is not linear, and we define the secant here between point P and Q as a line which joins these 2 points. So a line that goes from point P to point Q is called the secant. As you can see, when points P and Q they get closer and closer together, the orientation of line PQ changes. As you can see in this graph, the distance between the points P and Q is extremely small. This causes the secant to be a line that now we call the tangent. This line now is called tangent, which runs parallel to the curve in the same direction as the curve and touches the curve only at one point, which is point P. You just have to remember that this line, which is tangent to the graph, runs in the same direction as the curve. We do not call a line like this one, which crosses the curve only at one point, to be tangent, because it does not run in the same direction as the graph. We define the average rate of change or the average slope of a function f of x to be the same formula that we use to find the slope of a linear function. Remember, for a linear function, slope was defined as m is equal to y2 minus y1 over x2 minus x1. But remember, y2 and y1 were 2 points on the curve which were corresponding to the x values x2 and x1. So I can write this equation as f of x2 minus f of x1 divided by x2 minus x1. This is a familiar formula that you saw since grade 9. Now, if we change x2 and x1 to b and a, then this formula changes to f of b minus f of a over b minus a, which we call the average rate of change of a function between the 2 points b and a. Now, if we make the point b very, very close to point a, then the average rate of change is going to be called instantaneous rate of change. So we define the instantaneous rate of change to be the rate of change of a function at a specific point. This corresponds to when the b value is very, very close to a value. For example, if a function is given f of x and you are required to find the instantaneous rate of change at a point, let's say b or a, what we are going to do, we are going to find another point, let's say b, which is a plus a very, very small amount. Let's call it 0.01. This is just an example. Then we are going to use the previous formula and we will find the instantaneous rate of change, call it IR, to be equal to f of a plus 0.01 minus f of a over a plus 0.01 minus a. Remember, this is your b value. Now, if I simplify this one, I get f of a plus 0.01 minus f of a over, this is going to cross out with this a, so you get 0.01. This is going to give us the instantaneous rate of change of the function at point a using the formula. This instantaneous rate of change of any function can be found either using this formula, which is the slope of a line, or using the graph by drawing the tangent line at a specific point, or we can use the most accurate technique, which is to find the derivative of the function at point A. Now, to find the derivative of a function, which is the main topic of this course, we are going to start talking about the derivative in a future section. But at the moment, the only tool we have are either using this formula or using the graph of the function. In the first example, we have a balloon which is being filled with helium. The table here on the right shows the volume of the balloon after 3 seconds for 30 seconds. The first question is that what is the dependent and what is the independent variable? It is obvious that the dependent variable is V, which is cubic centimeter, and the independent variable is T, which is our time. And the next question is that what is the unit of rate of change? Remember, the rate of change is the change in the function relative to the change in time. Now the function is volume, so the unit of rate of change is cubic centimeter to second. The next question is, using the table, we are supposed to find the rate of change between 21 seconds to 30 seconds, 21 seconds to 27 seconds, and 21 seconds to 24 seconds. Now, if you want to find the rate of change between 21 seconds to 30 seconds, 21 seconds is here, 30 seconds is here. So we have to find the ratio which we defined previously. So we're going to say the rate of change, R, is equal to 4,186.7 minus 1436 divided by 30 seconds minus 21 seconds. If you evaluate this one, this is approximately 305.63 cubic meter, centimeter divided by seconds. The next rate of change that we have to find is between 21 seconds, which is here, and 27 seconds, which is here. You can see that the points P and Q, or A and B, are getting closer and closer together. So the rate of change in this case is equal to the value of the volume at 27 seconds, which is 305.1 minus 1436 divided by 27 seconds minus 21 seconds. And if you evaluate this one, you get 269.35 cubic centimeter to seconds. The next question was between 21 seconds to 24 seconds. So again, 21 seconds here, 24 seconds here. So again, rate of change is equal to 2,143.6 minus 1,436 divided by 24 minus 21. If we simplify this one, we get 235.87 cubic centimeter to seconds. The next question is, what is the significance of a positive rate of change in volume of the helium in the balloon? The sign of the rate of change tells us how the variable is changing. In this case, because it's positive, this means that the volume of the helium is increasing as time is going on. If it was a negative, then it means the volume is decreasing. The next question is requiring us to graph the information which is given in the table, draw a tangent at the point corresponding to 21 seconds, and calculate the slope of this line. In this example, we are going to use technology to plot the graph. Plotting the graph is very simple. We are going to draw our x and y axis, and on the x we are going to divide it into segments of seconds. So we have 3, 6, 9, 12, and so forth, up to the last one. And also on the y-axis we are going to divide it such that we are going to have all the corresponding volume of the balloon. The graph looks like the one which is shown here, and at point 21 and 1436, at this point we are drawing the line which is tangent, which is touching the curve at only one point, which is point P. Now to find the slope of this line, we are going to find another point on the graph which the line crosses. We prefer to find a point which is going to be the intersection of two grid lines. So we are going to pick another point which is point Q here, which is going to be the cross of two grid lines. And the reason that we are picking point Q is that it's very easy to estimate the coordinate of point Q, which is 16.5 and 500. So the average rate of change, or the slope of the line, R, is 1436 minus 500 divided by 21 minus 16.5. If we evaluate this, we get 208 cubic centimeter to second. Now, as you can see, this rate of change is positive, which indicates that the volume is increasing as time is increasing. Again, this is the average rate of change. This is not instantaneous rate of change here. The next question is for us to find the average rate of change between the following pair of points, -4 and -1, and 2 and 6. Very easy. We are going to say that the rate of change is 6 minus -1 divided by 2 minus -4, which is 6 plus 1 over 2 plus 4, which is 7 over 6, and we can just leave it as 7 over 6, the rate of change. In the next example, we are supposed to find the instantaneous rate of change at the tangent point, which is given here. Again, to find the instantaneous rate of change, we need to find the slope of this line. To find the slope of this line, pick 2 points, preferably the points which are on the intersection of the grid lines. We know that the coordinate of this point is given by 3 and 4. Another point on the graph which we can pick is this point, which is the intersection of the grid lines. This point is 1 and 0. So instantaneous rate of change here is 4 minus 0 divided by 3 minus 1, which is 4 over 2, which is going to be 2. And the units depends on the units of x and y here. The next question is asking us to compare the instantaneous rate of change at different points A, B, C, D, E, F, G on this graph. Let's start with point A. At point A, the instantaneous rate of change is going to be the slope of a line which is going to be passing through point A. Since from left to right our tangent at point A is going to be decreasing, so this means that the instantaneous rate of change at point A is less than 0, is negative number. When we get to point B, the tangent is going to be parallel to x-axis, so this means at point B the rate of change is 0. When we get to point C, the tangent to the graph at point C is going to have a positive slope. Since from left to right the function is increasing, so this means that instantaneous rate of change at point C is positive. At point D, the tangent is parallel to x-axis, so this means that the rate of change is equal to 0. At point E, again, the tangent at point E is going to have a negative rate of change since the function is decreasing. At point F, again, the tangent is going to be parallel to x-axis, so this means that at point F the rate of change is 0. And finally at point G, the tangent to the graph is going to be increasing. The function is increasing, so this means the tangent is going to have a positive slope. So G is greater than 0.